So before I start this video, I wanted to show you this picture right here. This is literally the picture of our sun. And this is an extremely important picture that shows us a solar spectrum. It basically shows us tiny absorption spectra of various elements in the atmosphere of our sun. Every little black line you see, that's a result of some kind of an element, such as, for example, iron, sodium, potassium, calcium, or oxygen even, absorbing the light and producing these black lines. Now, the reason this picture is important is because by doing this on a much grander scale, we can then start seeing this in a lot of stars in the Milky Way galaxy, in essence allowing us to learn about their evolution and potentially find siblings or partners of various stars. Today though, we're going to discuss a new discovery of a very strange star that doesn't just have a very good explanation to why it is the way it is, but also potentially creates a major problem for what we currently believe about supernova and about various massive stars exploding in certain ways. And so, hello wonderful person, this is Anton. Let's discuss this very strange star and its unusual origin, find out why it's so unusual to begin with, and more importantly, learn about what this means for modern cosmology. But first, a super short review of what we know about star formation and supernova. When it comes to the evolution of stars, we know that over time stars generally accumulate heavier and heavier elements. And that's because initially, stars mostly contained hydrogen and helium, but during a supernova, an intriguing process known as the R process forces lighter elements to become heavier and basically forms every other element in the table of elements. And though some of the heavier stuff requires additional processes, such as for example collisions of neutron stars, for the most part a lot of heavy elements can be formed through various star explosions, with additional supernova over time basically enriching further generations of stars with heavier and heavier stuff. And that's in essence our sun. It's a population 1 star that very likely was formed after at least 40 different supernova in the past that dramatically enriched it in a lot of different heavier elements that usually astronomers simply refer to as metals. But that's of course a simple explanation. It does get a little bit more complex depending on the actual supernova and even the shape of the supernova. For example, if it's not perfectly aligned or if it's not perfectly spherical, it's going to release certain heavier elements into one direction and not the other direction, which will of course influence the evolution of future stars, with more extreme examples of various supernova remnants potentially producing more extreme examples of stars. And though we generally understand how all of this works to some extent, there are still a lot of things that nobody understands just yet. And so in the last few years, some stars have been discovered to contain somewhat unusual elements or potentially ratios of elements that did not make sense right away. And though most were explained to some extent, that's not the case for the star we're talking about today. So here's what it roughly looked like back in 1999. This is not a new star, it was actually known to us for over 2 decades, and it's known as J0931 plus 0038. And it's a relatively close, low-mass star that's believed to be population 2, or basically the second generation star after the existence and the explosion of early stars in the early universe. This star is also not really in the galactic disk, and is currently located in what's known as the galactic halo, a region around the galaxy where we often find a lot of ancient stars, which also makes this particular place a perfect opportunity to try to study the evolution of galaxies or to try to understand how galaxies and the universe itself evolved over time. But normally most stars found here contain relatively primitive elements. They'll obviously contain a lot of hydrogen and helium, but also some of the more simpler elements such as sodium, carbon, oxygen, and maybe aluminium. There's not going to be a lot of complexity in these stars, but they will contain some stuff. Once again, a result of these super powerful supernova in the early universe. The events that we actually know very little about because these first stars have never been detected or seen anywhere. We usually call these stars population 3 stars, and you can learn more about this mystery in one of the videos in the description. And so one of these stars, roughly around 13,000 light years away from us, caught the eyes of astronomers, and mostly because of its unusual elements. Very unusual elements. It seemed to contain stuff that we've never seen anywhere in these proportions. For example, it didn't contain a lot of sodium or aluminium, but it was very rich in iron, nickel, zinc, and even strontium and palladium. It basically had all of the stuff that we've never seen in most of these relatively ancient stars, and especially in these super strange proportions. Now, it might not sound like super important, but it's actually really important because it basically suggests that this star was created from a very different molecular cloud. A cloud containing elements that we've just never seen anywhere before, as if it was created by something really strange. And the cloud that this was made from contained extremely different elements from literally every other cloud we see. For example, strontium and palladium abundance makes no sense whatsoever, with the overall abundance graph resembling something like this, with the only possible explanation being very unusual supernova. A supernova that occurred billions of years ago that for some reason formed elements in a different way from what we expect or from what we've seen so far. And even though the star has been known since 1999, it's only because of recent observations in more color that all of this became apparent. The star was very low in carbon, very low in sodium, very high in iron and zinc, with the only proposed explanation that currently makes sense being an extremely specific type of supernova we never thought was possible. A supernova of a very massive star with a total mass of about 80 solar masses. But today we know that this should be impossible. A star of 80 solar masses should not explode. Modern calculations suggest that it should just become a black hole by just collapsing into one without any major explosion. And that's because when it comes to supernova, they're generally divided into several major categories. For example, a white dwarf of a certain mass is going to go through what's known as a type 1 supernova, in this case leaving nothing behind. Stars of about 10 to maybe 25 masses are going to go through iron core collapse supernova, but overall be somewhat faint compared to more massive stars that can generally even end up in hypernova or produce a gamma ray burst. And these will usually produce either a neutron star or a black hole as a result, with more recent studies even physically finding evidence for black holes or neutron stars left after major supernova. But with more massive stars, things become more complicated. They should either just collapse, maybe producing a gamma ray burst, but no major explosion otherwise. Or if they become really massive, they can explode completely, leaving nothing behind through the process of pair instability supernova. But there is this gap in terms of mass of stars where we do expect the star to just basically become a black hole with no supernova produced whatsoever. And that's also why we generally don't find a lot of stars with masses over 50 solar masses, except for maybe some exceptions here and there. It's because these stars seem to just basically kind of collapse, disappearing in the process. And this is what we expect from a star with a mass of 80 solar masses. Yet the only explanation we have right now for the star detected in the Milky Way is basically a supernova of a star with 80 solar masses. And so at the moment, there is just no explanation to what exactly is going on. Yet a supernova of this type of a star does explain a lot of these unusual elements present here, because here it would essentially be a somewhat metal-poor source of elemental production that did not produce a lot of things like sodium, but produced a lot of heavier elements due to the power of the explosion, with that particular star potentially even being one of the first stars in the universe, the elusive population 3 stars. And so through this process of stellar archaeology, the researchers here identified something we never thought was possible. As a matter of fact, here they actually calculated the explosion itself, and it could have been so powerful that it would technically have enough power to blow up a smaller galaxy. And so if this was inside a dwarf galaxy, this galaxy would no longer exist. But if correct, this also implies we should be seeing more of these stars, because it's quite likely this nebula produced a lot of neighbors. And so if we can find more of these unusual second generation stars, this would provide evidence for this hypothesis, while also providing evidence for unusual supernova that a lot of these first stars must have gone through. But I guess for now that's pretty much all I wanted to mention. Until we find out something else about the star or find additional stars with similar properties, it's just going to stay as a bit of a mystery. But once we do find out something else, I'll follow this up with the next video. Thank you for watching, subscribe, share this with someone who loves learning about space and sciences, come back tomorrow to learn something else, support this channel on Patreon by joining channel membership or by buying the Wonderful Person t-shirt you can find in the description. Stay wonderful, I'll see you tomorrow, and as always, bye bye.